Introduce Stephan. So welcome everybody to our second virtual AI machine learning seminar for the fall. And we're delighted today to have Stephan Mandt, who's an assistant professor in our own department here in computer science at UC Irvine. Stephan got his Ph.D. in theoretical physics at the University of Cologne. He then took up a postdoc at Princeton University and also at Columbia University. And at Columbia, he worked with Dave Bly, who's very well known in machine learning, of course. After that, he went to Disney Research from 2016 to 2018, where he was head of the statistical machine learning group. And then he joined UC Irvine. We're very happy to have him join us in 2018. He's going to tell us today about some new work in variational Bayes and video compression. So with that, I'll hand it over to Stephan.
Thank you very much. Thanks, Porrick, for the kind introduction. Hi, everyone. Welcome to this lecture. So as Porrick already announced, so the title of my talk is going to be Compressing Variational Bayes. And for some of you, that might ring a bell. For those of you who are already familiar with variational autoencoders, there's already the paper called Autoencoding Variational Bayes. And so that already tells you that what I'm going to do here is I'm going to introduce a novel perspective on VAEs and latent variable models, and actually show you how you can use these kinds of models to do actual data compression, for example, compressing images or compressing videos. But maybe to kind of get started, let me start with something that I guess everybody here already knows pretty well, that deep learning already affects pretty much all areas of our lives today. We are very aware of that. But on the same point, deep learning has really become increasingly expensive. Right? In fact, there is sort of an exponential growth in the complexity and the number of parameters in current deep learning architectures. So the plot here is actually taken from some NVIDIA blog, and it shows you sort of recent architectures that have become popular over time and the way how they evolved in terms of their sizes. So there's, starting with pretty old architectures such as RedNet 50, and then going up to GPT-2. Now you realize that this is not even currently totally up to date because there's already GPT-3 out there, which has 100 billion parameters, right? I mean, this really tells you that parameters are growing at a massive scale, and that really becomes a significant hurdle when it comes to energy costs, for example, but also just the need for having expensive data collection procedures, and there are all sorts of different problems that are associated with very large models. So what I want to argue here is that there's a huge need for more resource-efficient machine learning. And what I mean by that is that current architectures are vastly consuming different kinds of resources, namely, first of all, computation. In other words, how many flops do you actually, does your algorithm carry out in order to process the data? Then they're also data inefficient in the sense that they need a lot of data. They're consuming vast amounts of data. And they're also very inefficient in terms of storage. And we'll hear more about that in the next slide. So basically, as I already said, there are different kinds of inefficiencies that I would like to talk about. And what I'm arguing here at the same time is that, in some sense, variational Bayes is the answer to many of these resource inefficiencies. And again, I'm going to talk here about different kinds of inefficiencies. I think I've already listed them, but here they are again. Data efficiency is about how can neural models extract more information from sparse data, right? And the solution here is that, being Bayesian, essentially building more informative priors and maybe transferring information from one task to another task could be a solution, such as time series models. So we'll talk a little bit about that. Then I'm actually mostly going to talk about storage efficiency, which is about, how can deep learning be used to compress model parameters or data? And as you'll see, that this is kind of really nicely tied to the framework of variational inference and variational autoencoders. And then if I have time myself towards the very end of this lecture, I will also talk about runtime inefficiency. In other words, which types of training paradigms, in particular in Bayesian machine learning, are the fastest or the best suited for resource-efficient learning, right? And I'll argue here that in some sense, variational inference is also the answer to that problem. OK. So let me get started and talk about data inefficiency, because in some sense, it's kind of the easiest way, the easiest kind of inefficiency to solve and the easiest one to explain. And I want to kind of start that from a well-known model by now that my postdoc Robert Bamler, who might be also on this call here, and I developed a couple of years ago, which is called dynamic word embeddings. So what is dynamic word embeddings? So imagine you're a historian and you're interested in studying the evolution of language. In other words, how do the meanings of individual words change over time? So the simplest thing that you could imagine doing is, you take a large text corpus, for example, Google Books, and you divide up this corpus into individual years. And then you're kind of training a word-to-vec model, like a word embedding model, on all of these individual years. So you have like word embeddings in the year 1800 up to word embeddings for the year 2008. So it turns out if you do that, you might actually not be able to, because the vocabularies are typically large, and oftentimes you suffer from data sparsity, right? I mean, it might be the case that in a given year, you don't even observe the entire vocabulary. And a very simple fix to do that is to combine this word-to-vec model with a probabilistic time series model in latent space, which is called a Kalman filter. It's essentially a model that was originally developed to trace the to smoothen out the noisy motion of rockets that you observe in the sky, to find a smooth interpolation curve. And instead of tracing rockets here, we're essentially using that model to trace word embeddings. Right? So this can be combined in a joint model, and this is this dynamic word embedding model. So once this model is set up, you can actually make these nice movies of how language evolves over time. So what you see here are a word embedding cloud from the 1930s. Let me actually play that movie again. So what you see here is all the words move over the 1930s, and we're highlighting the word broadcast, which moves from one region of semantic space into a totally different region. And initially, it's kind of a very generic word, and it's associated actually with distributed and scattered. And later, only the word broadcast gets its new meaning, where we associate it with modern media technologies such as radio, press, and so on. Right? And so our model does that at the same time for all the words, and it's doing it in a very efficient way because it's really sharing statistical strength across time. There are also other things you can do with that model. So for example, you can ask, what are the fastest moving words in the last 150 years? And then you kind of get an unbiased answer like this one. Let me actually highlight one particular example among all these 10 different words. For example, the word peer here, as you see, changed over time. So what the plot shows is on the x-axis time between 1850 and 2000. And then on the y-axis, you see the similarity of certain other words to the word peer. And you see that there's a group of nearest neighbor in 1850, which are kind of nobleman, lawyer, knight, and so on. So words that characterize almost like a very high social status. And then those become less similar over time. And another group of words become more similar over time, which are the blue words. And those are kind of almost the opposite words. They are indicating people of equal standing to you. And so you can really see that the word peer underwent a dramatic change. And we do that for all the words in the vocabulary simultaneously. I should mention here that there's actually a nice browser that Robert Bamler built, which is also linked to our group website that you can play around with. So why is this actually a good idea, building such dynamic word embedding models? So it turns out that without temporal smoothing, if you only train separate word-to-vec models and you just kind of trace the evolution of language, then the signal essentially gets lost in the noise. So in order to highlight that, so we show two different word embedding clouds at two subsequent years. So this is 1999. And now I'm showing a word embedding cloud of the year 2000. And I'm essentially connecting the word embeddings between these two consecutive years with differently colored lines. And what you see here is that this is essentially kind of a big, big mess. Everything at the same time moves. Basically, there's nothing to be seen here because there's so much noise and so much randomness in the evolution of words that it's very hard to find anything interpretable about that. But if you do it with dynamic word embeddings, there's actually a strong prior for kind of staying in the vicinity of the previous meaning of these individual words. And you're suppressing a lot of that noise. And you see that the only significant changes remain, right? And most of the words are more or less static, right? And so this is a very good example of why clever design of priors, and in particular Bayesian machine learning, can help you with the problem of data inefficiency. You can effectively work with much less data and get similar results as if you had a much bigger data set. So before I get to the next topic, I also want to talk about another popular class of models that I'm actually working a lot with, which are called variational autoencoders models. And variational autoencoders are so-called deep latent variable models that allow you to, first of all, analyze and find hidden structure in highly structured, dense data sets, such as images, and also to compress them, as we'll later see. So what is this model going to be about? So you see on the left-hand side, this is the so-called generative model, where you have a low-dimensional vector of noises. and you push this vector of noises through a, say, trained neural network. And this neural network is trained in such a way that it transforms the lower dimensional noise into a highly structured object in the data manifold. Now, the problem with these models is that you have to simultaneously train these networks. So you have to learn theta. And this is only possible if for every given image, you essentially know its underlying noise distribution. Right? So in other words, you have to learn or infer the posterior over the latent variable z and simultaneously train the generative network theta. And this is, in fact, most efficiently done by fitting what's called an inference network to that model in such a way that given a data point, an inference distribution spits out the optimal distribution over latent variables. And then you're using variational inference. In other words, you're matching Kalb-Kleibler divergence between that inference model and the original model's posterior distribution. And it's called a variational autoencoder because there's essentially a closed path from the data through the inference network to the noise distribution z, and back to the data through the network with parameters theta. And we'll encounter that many different versions of this model as we move forward. So my path to compression was actually pretty nonlinear, and it started really with interests in fundamental research. So when we were still at Disney Research, I had an amazing intern, Yingzheng Li, who is now a researcher at Microsoft Research. And we were interested in a problem of fundamental importance, namely, can we actually disentangle static information from dynamic information in short movie clips of, say, cartoon characters that are walking or other kinds of short movies, right? So what you see here are different, so-called sprites variables, which are generated by the model. And as you see, they're all looking differently, and they're all walking in different ways. And now the question was, can we learn a latent representation using something similar to a variational autoencoder, such that we disentangle the static information from the dynamic part? And the answer is yes, and it actually relies on just kind of a clever architecture of the probabilistic model. So and this is actually shown on the right here, where you see, first of all, the sequence of frames, x1 through xt of the video. And then you see there are two sets of latent variables. The first one is a global variable f that actually influences all of these individual frames. So we hope that this here encodes static information, such as clothing and hairstyle. And then there's a lower dimensional latent time series, z1 through zt. And every zi is only responsible for explaining frame xi, right? And so we hope that this here encodes a lower dimensional representation of the dynamics. And it turns out that it works. So if you kind of train this model on these videos, you can separately generate videos by conditioning, for example, on f and only generating different latent time series. Then you get these videos. Or you fix the time series and you sample different f's, and then you kind of get characters that are all looking differently but carrying out the same motion. And you could do other things with it. For example, given the trained model and given a set of data points, you encode them, and then you're swapping one of these two latent variables and replacing it by something else. So for example, if you swap the dynamics part and decode again, you kind of preserve the appearance, and you're sampling different motions. So all of those here, if you compare them one by one, they are looking the same, but these characters are carrying out different motions. And you can do the same thing also with swapping out identities while preserving the dynamics. So the next question that we then asked was actually, can this be useful in any practical application? Remember, I was back then in an industry research lab and always kind of keen on applied research. And I thought, actually, if we have a strong model that is actually capable of predicting future sequences of videos, can that be used in image compression, or in video compression, right? And then we kind of read a couple of papers, and we came up with this paper at iClear by Johannes Ballet and others, which essentially proposes to use conventional variational autoencoders for image compression. So the way it essentially works is you take a pre-trained VAE, you take an input image, you encode it. This gives you a vector, a mean encoding. And then when the model is trained, you essentially have to quantize this latent state. Then you get something which is called z-twiddle, which is now discrete. And you can use the model's prior p of theta to entropy code it, right? Such that you now have a very compact code of zeros and ones. And if you want to unpack this code, you again take the prior, you convert it to a discretized latent state z, and you use the deterministic decoder to convert it back into an image. So essentially, we adopted the same idea, but we had applied it to video. And in particular, we used our global and local split such that we hope to find essentially information that characterizes the entire video and then separate that out from information that encodes dynamics. And it turns out that this is actually pretty related to what's called a keyframe. Namely, a keyframe is sort of a reference frame in traditional coding that tells you something about the entire couple of next frames that are going to follow. So this ended up in my first kind of paper in compression, NeurIPS 2019, and it was called Deep Generative Video Compression. So I don't want to oversell this here because actually we came up with much better approaches. So this was actually kind of more of interest for historical reasons, because the first architecture didn't really scale very well to high-dimensional videos. So we only looked at low-dimensional videos like those here. And we also only trained and tested on similar content. Right? So it turns out that there are amazing compression gains if you train and test on very simple videos, for example, a moving robot arm. Then you kind of get these results here, which is so-called rate distortion plots, where the x-axis shows the bit rate, in other words, the file size of the given video, and the vertical axis shows you the average error that the model is doing, in other words, the reconstruction error, actually the inverse reconstruction error. So you want to be at low file sizes and at high inverse reconstruction error. So you want to be in the top left here, and you see that with the solid lines, you're actually pretty much there. So those are our kind of different neurocodecs, and the classical codecs are sort of down here. Again, as I said earlier, this is only kind of the first model on low resolution video, but we'll show you more impressive results as we go through the lecture. OK. So to teach you a little bit more on compression and tell you more about the more recent activities in my group, I feel that I have to dive in a little bit more deeply and tell you about variational inference, which is sort of the working hose of all of our compression work. So what is variational inference, and what is, in the first place, Bayesian inference? So Bayesian inference is a statistical approach to machine learning, which relies on the statistical notions of uncertainty due to Thomas Bayes, who's depicted here. And the idea is that you have a model that corresponds to a joint distribution over what's called latent variable z here that we've seen before, and data points x. And they kind of can always be written in the form as a product over a likelihood and a prior. What we're interested in is the so-called posterior distribution, P of z given x, which is how do our latent variables change as we observe more and more data. So as many of you know that this posterior is very hard to compute, in particular for high-dimensional models, and we need tractable approximation schemes to do so. And in order to do so, we decide on a class of approximate posteriors, Q of z. So this is another set of functions. And they have tuning parameters lambda that we use in order to match this distribution to the posterior. So this is the picture that you should have in mind. The Bayesian posterior could be this more complicated bimodal distribution, and we're using in this example a simple Gaussian distribution, and we fit it as good as we can to that more complicated distribution, right? And now in this example, for example, the variational parameters are the mean and the variance of that Gaussian distribution, and we can tune them to achieve the good matching. And in more detail, what we actually do is we're minimizing Karpal-Kleipel divergence between these two distributions, which is a sort of information theoretical distance measure. Let's have a closer look at the objective function that variational inference optimizes. And this is called the so-called evidence lower bound, because it's a lower bound to the logarithm of the marginal likelihood of our data. So usually we'd like to think of that as two different terms, and let me actually explain them to you separately. So one of them is called distortion terms, in other words, the expectation under Q of log P of x given z. And the other term is sometimes referred to as the rate, and it's the KL divergence between your variational approximation Q and your prior P of z. And note that in variational inference, we usually have beta equals to 1 here, but in this context of compression, it's oftentimes convenient to kind of consider the more general, not necessarily probabilistic framework. So what do these two different terms do if you optimize them separately? So if you only care about distortion, you can easily convince yourself that you learn a model that places all its probability mass to only explain the data as well as possible. So in other words, if you only optimize the first term and you have kind of any flexible function Q that you can choose from as you like, the model will decide on a delta distribution that places all of its probability mass below the maximum likelihood solution of that likelihood. And it turns out that in the presence of this rate term, beta equals to 1, the solution actually prefers something more entropic, and these two terms really conspire in such a way that you achieve this nice matching between the variational distribution and your variational and your true posterior. Okay. So how does this variational inference in particular connect to compression? Why is there a connection between compression and variational inference? So to understand this a little bit more, we have to, again, look at the compression pipeline of using, again, a trained variational autoencoder for image compression. So this amounts to taking different steps. So in the first step, you're finding a latent state, Z, for using the trained model and given a data point X. And typically, you kind of use the most likely value of Z, which corresponds typically to the mode of your Gaussian posterior distribution. So we call that Z. However, if you want to do lossless compression on top of that, we're not done yet, right? We cannot compress dense vectors, so we have to quantize them. And so this actually happens in the next step. So you decide on a discretization scheme, and typically you round to a certain number of decimal places. And so you kind of take your discrete Z and you round it to some number of decimal places. And then in the third step, we still have a dense vector, like a large vector with many integers. And we still want to kind of remove any remaining redundancies in that scheme. And so now you use the prior P of Z in order to entropy code the latent state. And we ultimately end up with a compressed bit string. Right? And now, as you might know, the expected code length is exactly measured by the mismatch between the empirical data distribution, expressed by Q here, and the model that you use for entropy coding, which is the prior. And so therefore, the scale term really measures the expected code length. And as you very well know, is that there's always a trade-off between reconstruction and compression length. So this is also sometimes referred to as the rate distortion trade-off. And we'll see many examples as we move forward. So basically, you can do different kinds of compression using these VAE and approaches, and more generally, variational inference in Bayesian deep learning. We've already talked about image compression, where you really compress and quantize images. But you can also quantize models. So for example, think of the word embedding model that we've found before. If you had a notion of uncertainty associated with these word embeddings, you could also use similar tricks to compress the model. In other words, the word embeddings, and also come up with a more compact bit string. And we'll actually see examples of that also. So as the first real research contribution on compression that I want to talk about here, I want to talk about a paper that we just published at ICML this year. And the question that we were addressing here is the following one. So if you're familiar with the, if you look at the current compression literature using variational autoencoder models, you'll see that none of them are actually explicitly using posterior uncertainties. And so the question here is that, can we actually really use posterior uncertainties to arrive at a better algorithm for image compression? And so this is going to be answered in a minute. And to kind of motivate this from a slightly different angle, I'm actually adopting here a very nice slide from Robert Bamler and a nice example that he came up with, which essentially shows you that when we as humans communicate about data, we're already automatically including our degree or our belief about uncertainty in our human language. So for example, if you ask me what is actually the population of Rome, and then I might look it up in the Wikipedia and give you the exact answer, right? On April 30th, the population was 2,879,728. But then your friend says, well, I was actually referring to something else. I was referring to the year 500 AD. And then I might look up the internet again, and I come up with a different answer. And this time I'm telling you, this is 100,000, right? So why does it make sense? I mean, suddenly I'm being much less precise here, right? And of course it makes sense, because when we talk about numbers, we automatically include our uncertainty estimates in them, right? And of course, there's much more uncertainty and maybe also less relevance about knowing the exact population of Rome like a few hundred years back. So we want to teach machine learning algorithms to do something similar when it comes to image compression. And this actually relates to another question, namely, in some sense, compression algorithms already take uncertainties and take probabilities into account. And here I want to highlight that we're talking about a different kind of uncertainty and a different kind of probability. So it turns out that in the paradigm of compression is actually already don't transmit what you can predict. So in other words, when you can predict the next frame of a video with very high accuracy, there's not so much you have to remember on top of that, because usually you only remember differences from your prediction. And this is kind of already used in current models, namely better, as I said, better generative models that are more accurate already have better compression rates, because they're essentially modeling the data distribution. And we know that the bit rate of a compression model is always determined by essentially the probability of the data under our model, right? So this is already sort of done. So what do we then different? What then is it that we do differently? So first of all, before I answer this question, I want to show you how current lossless compression schemes exploit probabilities. And this, I'm going to tell this in some detail, because it's going to be important to understand our innovation of how we exploit that for compressing images. So I want to give you a classical example of arithmetic coding, which is a popular scheme for compressing the outcome of say a 10-folded dice in a most efficient manner. So let's assume we have like 10 different outcomes, 1 through 10 different messages. And they all have like different probabilities that might be distributed as shown here. And let's assume we have a prior belief over how these probabilities are distributed. So how does this arithmetic coding work? The first thing that it does, it's actually computing lower and upper cumulative distribution functions. So what do I mean by that? I'm essentially summing up all of these events and their probabilities up to a certain event that I observe, say 4. And if I do that, including the event 4, I'm going to kind of get the step function, which is shown here by the dashed lines. And if I'm doing it except, so everything before 4, then I would kind of get the lower cumulative distribution function, which is the solid line. So now what you see here is that this gives us a mapping from discrete outcomes to intervals on the axis of 0 and 1, on the subintervals of 0 and 1. And coding now works as follows. If I'm observing an outcome, for example, 7, I'm looking up the corresponding interval, which is the difference between the upper and the lower cumulative distribution boundaries. And so this specifies an interval, a subinterval of the interval 0 and 1. And I can take any member of that interval to encode the outcome. Right? So this, like, the outcome is uniquely specified by any number in this interval. And among all of the possible choices, I'm picking the member that has the fewest number of decimal places. Right? So here I take 0.111 in binary notation. This is the shortest description of a number in the interval that's describing our uncertainty region associating with the draw 7. Right? So this would be our encoding. All right. So we want to do something slightly different. So our paradigm as we move forward here is to not transmit what we are not sure about. So this is something different from we're not transmitting what we can already predict. We want to explicitly encode our uncertainty. And we want to do it in a similar fashion as we did for arithmetic coding. But actually, before we get there, let me kind of give you a more kind of Bayesian way of thinking about it that hopefully might be very familiar to those of you who are already familiar with Bayesian thinking and Bayesian machine learning. So let's imagine we want to compress a very simple model, which is just a linear regression. Right? So here we have data points, which are just scalar x and y pairs. We assume that there's a linear connection between them. And we want to fit a linear regression model characterized by an offset a and a slope b. Right? And so that model, for example, could be that green line over here. So how would you do that? I mean, first of all, we would go in parameter space, where we indicate a and b in the joint space of all a and b combinations as a single point. Right? So this is now our model that corresponds to the linear regression model. The first thing that we have to do is we have to quantize. And so we decide on a quantization grid. And then we would typically represent the model as the nearest quantization point, like this one here. Okay? And then if we reconstruct the model, we will typically encounter an error, which comes from the quantization. And like the resulting fit will no longer perfectly fit our original data as used before, but it's still kind of a decent reconstruction of that model. The question is, can we do better? And the answer is, of course, we just have to be Bayesian. When we do Bayesian linear regression, we know that instead of only looking at the point estimate of model parameters, we have an entire posterior distribution available. And oftentimes, this posterior distribution has an unequal shape, right? So here there's much more certainty about the slope A than there is about the offset B in this example, right? And so what we can do now is we can pick different quantization grids. For example, quantization grids to different precision values. Some of them are more expensive than others because they amount to memorizing more decimal places than others. And now there are various trade-offs possible, right? So for example, there might be certain grid lines correspond to 3 bits, others to 2 bits. And what we typically want to do here is we want to pick a grid point that is relatively cheap while having a high probability mass under our posterior distribution. So instead of picking this one here, we're now picking that one because our posterior has more probability mass in this region. In other words, we're investing more bits to encode A, and we're investing fewer bits to encode B. And this is exactly very intuitive what we should do. And then if we kind of go back and reconstruct, it turns out for a comparable number of bits, we get actually a much better reconstruction, right? And so this is the whole idea. So this is what we want to do in the arguably most simple and most general fashion for any model and any variational posterior. OK. So how does this work? It's actually very tightly connected to this idea of arithmetic coding. And that's actually the reason why I spent so much time in explaining that arithmetic coding algorithm to you. So the first thing that we could try now is like, can we generalize arithmetic coding from discrete events to something continuous? Right? And let's see how far this analogy gets us. So the first thing we do is we start with a prior probability distribution over events. So this is here this now continuous Gaussian line here. And as before, we compute its cumulative distribution, which is now the orange curve here. And that allows us to kind of go back and forth between the space of latent variables z here and the interval 0 and 1. And let's imagine we make a certain observation, like we observe this outcome, and now we want to encode it. We would do the same thing as before. We would sort of look up its position along the CDF and map it to a point now between 0 and 1. And now, big trouble. This point here, in general, has infinitely many decimal places, right? It's an event of probability 0 that this would actually have a finite number of decimal places. In general, this is just like a real valued number, right? And so, and of course, now we cannot proceed, right? I mean, now there's no simple way of how we could have any gains from it because, storing all the digits of a real valued number is just as expensive as storing the original image, for example. So the question is then, can we do something similar as before? And the answer is yes. Remember, in variational inference, we're not only left with a point estimate of our latent representation, but rather we have an entire variational posterior distribution Q available, right? So now we have that Q. And this actually has a maximum mode, which is mu I, but it also has a certain variance, which is plus minus or sigma I, associated with that observation zi. And now essentially what we do is we are kind of mapping this entire interval through the cumulative distribution function to another uncertainty region, which is now a subinterval between 0 and 1. And again, as before, any number that is within this interval here is a valid encoding of our observation, right? Because it's kind of reflecting the posterior uncertainties that are coming from Q. Now the question is then, which member do we use? Well, first of all, again, we want to use binary representations with as few decimal places as possible. But now they're kind of no longer strictly well-defined. So for example, we could pick this one here, which has 3 decimal places, 0, 1, 1, 1, which corresponds to 7 divided by 8 in binary notation. And if we use that, we actually kind of get a reconstruction which is closer to the mode, right? Because that dashed line here has higher values in its vicinity. But we could, for example, also choose to use 0.11, which has 1 decimal place less, so it's kind of cheaper to store. But it has a higher distortion because it's essentially, its decoding is further away from the posterior mode, right? And those are now trade-offs that we have to play around with. So actually, all sorts of trade-offs are possible here. So now we have not only a one-on-one relationship between an observed outcome and a corresponding code as in the discrete setup, but now we have, for any given variational posterior distribution, we have an entire rate distortion trade-off curve that we can exploit. Right? But this is essentially the idea of how we go from there to there. what do we do if we're working with not one-dimensional ZIs, but if we actually want to compress a latent variable that comes, for example, from an image, and that might have, whatever, millions of components? Well, the nice thing is, as long as you work with factorized variational approximations, it turns out that this optimization problem, this trade-off, decouples over dimensions. So you can basically treat every dimension ZI of ZI independently and compute its own rate distortion trade-off in its own optimal encoding. OK. So this was kind of very fast describing this method that we called variational Bayesian quantization. And let's actually look at how well it performs on various different models. So one thing I want to highlight here is really that this is not particularly a method only for image compression. It's really a method that is kind of very fundamental and that allows you to compress any trained model, the only restriction being that you used a Gaussian variational posterior in post-processing, right? And in particular, to show you that how versatile the model is, we looked at a model that is not very often compressed in practice, namely word embeddings. Right? So what do we plot then here? So remember, in Word2Vec, there are certain evaluation tasks that you do in order to determine the quality of your embeddings. And oftentimes they're called, they relate to looking at word embeddings and their relationship, their geometrical relationship, and how well you can use them to reason about facts that you expect to be true in language. So for example, if I use the word embedding model for king, I subtract the word embedding for man, and I'm adding the word embedding vector for woman, I'm sort of expecting to get queen out. Right? And this here, the y-axis tells you how oftentimes is this actually the case, how often, or is my correct answer among the 10 highest scoring answers that the model offers. Right? So this is called hits at 10. And now what is the x-axis? Well, this is just like how aggressively we compress, right? So remember, we can do that. And in the simplest baseline case, what we do is we simply round our word embeddings to a certain number of decimal places. And now we end up with a discrete vector. And we can use off-the-shelf lossless compression tools on top of that. Right? So this is essentially what you get. So we kind of tested, we compressed we rounded the model to different levels of aggressiveness, from very aggressive here to very little aggressive in this regime. And then we kind of combined it with tools like gzip and so on, and just measured the file size, right? So this kind of gives us the bits per latent dimension. And then we also measured how well do these models perform? How much valuable information have I lost through the quantization procedure? And it turns out that if you do the same thing with Bayesian arithmetic coding for the Bayesian formulation of Word2Vec, you actually do significantly better. So you can kind of maintain a lot of that performance at much, much smaller bit rates. Right? And so this, again, is using that paradigm of not transmitting what you're not sure about. There might be certain dimensions where there's a high degree of certainty, and you don't want to round there. But there might be other dimensions where the model is very unsure itself about the right encoding or the right embedding. And those are the places where you want to round more aggressively, right? So it's kind of an uneven data-driven way of rounding, if you will. So interestingly, you also get pretty good performance if you look at image compression. And remember, this is all in post-processing, right? So we trained a variational autoencoder. And then we were kind of just curious about, for that trained variational autoencoder, how well can we actually compete with image compression models that were specifically designed for image compression in post-processing, right, using our variational Bayesian quantization method. And to this end, we again looked at rate distortion curves. So again, this here is the rates, the average bits per pixels, in other words, a measure of the file size from high file sizes to small ones. And this is PSNR, which is, again, an inverse distortion measure. So first of all, we have sort of a gold standard here, which we never expect to beat, which is a model by Ballet et al. From 2017. And Ballet et al. Really trained separate models. So in other words, separate neural networks for every point here on this rate distortion curve. Right? So this is kind of not a single model. Those are kind of many different models for different parameters of beta, as you remember, which allows you to tune the rate distortion trade-off. And what we did is we picked only a single model, using exactly the same architecture as Ballet. And then we checked how well can we quantize that model in post-processing. And that actually resulted in that orange line. So we don't get quite as high performance as here, but we're getting pretty close to it. And in order to check if that's actually a trivial result or something interesting, we also compared it against JPEG, which is arguably still a useful even not a state-of-the-art image compression model. And this gives us this rate distortion curve here, the gray ones, right? And so we're better than JPEG, but we're not quite as good as the best performing image compression models, where, again, every point here corresponding to a different model. And the other baselines, which are arguably more important, is kind of how well does this approach compare to just quantizing the latent states differently and then doing the lossless compression on top of it, right? And the short answer is we do much better, right? I mean, any kind of even or even sophisticated way of doing it will kind of result in worse rate distortion trade-offs. Okay. So last thing I want to talk about this model here. What I want to talk about this model, sorry, the last aspects of this model that I would like to cover here are its qualitative properties, and they're pretty interesting actually. So everyone knows that when we take a compressed image, what happens when you actually make the compression more and more aggressive. So essentially, you get these kind of block artifacts. And ultimately, at some point, you won't realize the image anymore because it's so noisy or there's so many block artifacts that you cannot see anything. So in our case, something very different happens. So if you start with an encoding of MNIST digits, for example, 4 or 5, doesn't matter, and you're kind of investing fewer and fewer bits to compress it, you're actually starting at some point to confuse these different digits, right? And at some point, you're always decoding the most generic digit, which is the one that's sitting in the middle of your latent space. And interestingly, that also works for faces. When starting with 2 different faces, you're kind of investing fewer and fewer bits. The quality looks pretty OK, but at some point, you're always decoding a generic face. So we found that to be a pretty interesting artifact of the approach. Yeah, another one is that mode collapse doesn't actually harm your model at all. It turns out the model invests 0 bits in collapsed modes, which can be pretty practical if you apply that for model compression. OK. So the last part of my talk, I want to talk about another compression-related paper by the same authors, Ivo Yang and Robert Bamler, who are in my group. But this time, it was actually another project, which we just got accepted at NeurIPS. And it's still about probabilistic inference perspectives on neural image compression, but this time with a slightly different flavor. So essentially, what we're trying to establish in this work is a new view on compression, namely to say that compression is a way of doing probabilistic inference. And to understand that a little bit better, let me tell you something about traditional codecs. So in classical compression, you oftentimes have a unique pre-specified decoding protocol that essentially determines the code in some way. I mean, this is really your codec, right? It tells you how to go from sequences of bits or a bit string to a high-resolution image. However, the encoder is oftentimes not specified, right? Everyone can come and say, hey, I actually have a better encoder for a given decompression algorithm. Right? And so having a unique decoder and not necessarily unique encoders ensures interoperability between the different implementations of your codec. So some codecs can be fast, or some encoders can be faster and therefore not giving you the expected quality back. And others kind of invest more time to find a good encoding, but are therefore slower. And to kind of give you an example, there are different implementations such as PNG Crush or Image Magic, and they both have like different trade-offs along efficiency and quality, if you will. So in this view, decompression is really probabilistic inference. So given a unique decoder, we want to infer an image's optimal latent representation. And now it's actually a very straightforward thought that, as we know more about variational inference and we know tricks of the trade of variational inference, and given that variational inference and compression are so tightly connected with each other, it should be easy to come up with better inference schemes that lead to ultimately better compression algorithms. Right? And so the hope then is to open up a new VI toolbox for image compression such that you can use more advanced techniques from the variational inference literature to actually gain performance improvements. So what we did is this time we were really looking at state-of-the-art architectures for image compression. And we were looking at models that reported the best rate distortion trade-offs that were out there, right? Better than classical compression, for example. And it turns out that all of these models make use of a hierarchical VAE architecture in the sense that we have data X, we have latent variables Y, and then we have what's called a conditional prior, which means on top of Y, there's another latent variable Z. And that Z sets the scale and the shape, the mean and the scale of the conditional distributions of Y given Z. such that you can actually ultimately encode your image with fewer bits, right? So this hierarchical structure essentially guarantees that your entropy coding part will be more efficient. So how do you train these models? So first of all, encoding in the trained model is very simple. You use your amortized variational inference networks, F and FH. You kind of output a mu and a mu z, and you use them to, you round them, and this gives you kind of a latent state z hat, and then and this then results in a latent state y, and those two together allow you to encode your image. And during training, you're doing kind of the same thing. The only difference is that instead of rounding, you're actually injecting noise, and that noise injection somehow leads to a more robust encoder. So what we propose is something different. So we basically adopt the same architecture, but we are just not happy with that kind of one-shot solution that an amortized variational inference approach gives us. Instead of doing that, we're kind of going back to the classical EM procedure of iteratively optimizing over mu and z, mu y and mu z, and thereby kind of getting better latent representations for a given image. So I'll explain that a little bit more in more detail in the last couple of minutes. So to understand the procedure a little better, let's actually understand where that inspiration came from, at least from my side. So I published a few years back a paper at ICML with Joe Marino and Yisung Yu on what's called iterative amortized inference. So the idea is that in amortized inference, you typically have an elbow, an evidence lower bound, where you're kind of, as a function of your variational distribution Q here, you really aim to optimize certain neural network parameters phi that in a one-shot fashion predict the optimized latent variables, the optimized variational parameters for a data point xi based on the features of the data xi. Right? But this is actually already kind of amortized inference. If you kind of lived before, if you knew about variational inference before the deep learning revolution kicked in, you were kind of more used to a different kind of variational inference, namely where you understood the elbow directly as a function of the variational parameters of your Q distribution. In other words, for every data point, you would optimize its mu and its sigma in a gradient descent fashion. And this is pretty much shown here. So this is the elbow contribution of a single input image, x, and it tells you that using gradient descent, you can actually optimize that particular image's latent representation. And so what's done in this paper is actually to, again, amortize this procedure in a different fashion, but that's not really the aspect that we were interested in. We were really interested in this kind of gradient descent-based improvement of the latent variables. So in particular, why is this paper interesting? It kind of offered three new ways of how you could actually improve conventional image compression, neural image compression, with ideas of variational inference. And these different three angles relate to known effects in VI that correspond to different suboptimality gaps. So the first one is called amortization gap, and that's exactly what I was just talking about, which kind of tells you that instead of optimizing your elbow over your parameters of your inference network, you can actually better directly optimize every variational distribution's local variation parameter lambda. And the difference between the two elbows is called what's called the amortization gap. In other words, the imperfection coming from the amortization procedure. Yeah, this can be solved by doing iterative inference. Another very original idea that Ivo came up with and tried out was to also eliminate another gap, which we called the discretization gap. And so the idea here is that usually what you do is you kind of you work with some sort of real valued variational distribution. And then later on, you kind of when you use that model for compression, you're kind of rounding the latent states and evaluating your elbow on the rounded latent states. But it's actually much better to directly working with a discrete representation, for example, using modeling Z as discrete and applying what's called the Gumbel softmax annealing technique. And again, I cannot really go into much detail, but this is what we call the discretization gap. And then finally, so this is kind of the most advanced idea, there's also a marginalization gap, which comes from the fact that in a hierarchical model as this one, what you really want to do is you want to encode your latent states y using the marginal prior p of y. But p of y is really the integral over all possible z's of p of y given z times p of z. And that, again, is an intractable quantity. So you cannot compute that integral. And so what people do in practice then is they kind of use variational inference to lower bound that integral. And so the gap that is a result of that procedure is then again called the marginalization gap. And it turns out that there's a procedure which is called bit spec coding that you can actually use in order to close that marginalization gap. It's actually a trick from lossless compression, which for the first time we actually got to work in a lossy compression setup. And again, this is way too much to talk about here in this lecture. So since I only have a few minutes left, let me maybe talk about the results. So we tested against very rigorously against a whole large list of different baselines. We proposed 2 different methods of our methods, 2 different versions. One is using bit spec coding. The other one is not using bit spec coding because there are certain disadvantages. There's some additional complications from applying bit spec coding, even though it kind of gives you, it closes the amortization gap, but I mean there are also downsides to it, and that's why we have 2 versions here. And besides these many different baselines, we also looked at various ablations, and it's probably too much to talk about all of them in detail. So let me directly go to the most important performance plot here. So this is, again, a sort of rate distortion plot, but this time we're looking at something slightly differently. We're looking at rate savings relative to a certain baseline, right? So we say one model is our baseline. So in this case, it's the best classical codec, which is BPG. So the relative improvement of BPG to itself are 0. So that's why the BPG codec is the flat line here. And then all of these other approaches here, they're either better or worse than that baseline. And in particular, they show different behavior as a function of the PSNR value. In other words, are you interested in the high quality setup where you're kind of investing a lot of bits for kind of having high resolution results? Or are you interested in the low resolution operational mode in the or low bit operational mode of your compression scheme? And so long story short, we actually get pretty solid performance improvements. Remember, we're not changing anything about the model. All the model architecture details are exactly the same. The only thing we're really changing is the inference procedure, given the trained model. So we're allowing a little bit of extra time to fine-tune the variational parameters of a given image. And this then results in the blue and the orange curve, which are our results. So this is the bit spec result, the slightly better one. And then the biggest performance improvement actually comes from this stochastic Gumbel annealing, in other words, closing the discretization gap idea, right, which is orange. And then, the base model without doing any tricks is essentially the brown line here. And you see that this is kind of pretty much on par with the best performing classical codec. So that actually right now is the state of the art in image compression. So let me also give you a couple of qualitative results that we came up with. So here, this is like one of these popular images that people look at, like a high resolution photo with some region zoomed in. The important comparison here is actually the last and the second to last plot. So this here is a classical codec. And here, this is the base model. In other words, the model in which we do amortized variational inference, proposed by Minnan et al. In 2018. And this here is our improvement gained by only doing the iterative inference procedure and closing these various gaps. So what you see here is, you actually get much better quality, and all of these kind of details that show up in the face are suddenly coming out of it. OK, so this should be NeurIPS 2020. OK. So let's see. Strictly speaking, I have 5 minutes. I usually like to also have time for questions. But let me very crudely tell you in 2 minutes about the last thread of my research. I also work on accelerating variational inference to improve its scalability and its usefulness and practical setups. I care about hybridizing Markov chain Monte Carlo methods with variational inference. We had this kind of paper on essentially converting stochastic gradient descent into a variational inference scheme, and thereby operating with much larger step sizes to effectively sample from the posterior, even though you were just running gradient descent. And finally, most recently, there's an interesting paper that I, again, don't have time for, which is this idea of cold posteriors, where we're really questioning the paradigm of Bayesian deep learning. So it's not that point estimation is always better. Usually, a point estimate is a better model than a strict Bayesian deep learning model. But if you kind of lower the temperature in what's called Langevin dynamics, and you're kind of working with a downscaled, with a lower variance version of your Bayesian posterior, you usually do better. You do better than point estimation, and you do better than strict Bayesian inference. And I think this work is pretty interesting and has a lot of open questions associated with that. So with that, I would like to close. Let me go to my summary. I don't have a summary. Oh, yeah, to my summary page. So this is really work of many people. In particular, I talk mostly about work by Robert Bamler and Ivo Yang, who were kind of working on this image compression, the two most recent image compression tools. Robert has also worked on dynamic word embeddings, and he's actually now becoming a professor in Germany in Tübingen. And then I also have results that I didn't talk about, which are on video compression that I actually didn't cover today. So kind of to wrap up, you can get, I talked about posterior refinement using iterative amortized inference. I talked about exploiting posterior uncertainties in doing Bayesian quantization and post-processing. And I also talked about iterative inference for image compression, which essentially closes the gap between variational inference and really converting it into useful novel compression schemes. So with that, I would like to close, and I'm here available for questions. Thank you.
All right, let's give Stephan a virtual round of applause here for his talk. I don't know if anybody can hear me or not, but I'll assume so. Let's see, maybe there's time for a quick question or two before people have to run at 2 o'clock.
Can I ask? So thanks, Stephan. Great talk. And by the way, congratulations, Robert. And one thing I was wondering about is, so you use the model uncertainty, right? So uncertainty about the model parameters for compression, but then what you test for is error in how the model behaves on inputs, right? What are the outputs of the decompressed model? So I'm wondering if there's anything to say about how this uncertainty in the model translates into uncertainty in the outputs of the model.
Yeah, that's a good way. I mean, you can essentially the way I think about it is essentially we're using the posterior uncertainty as a measure of how aggressively we can round a latent representation, right? I mean, if the quantization grid is kind of much more so basically, if there's a dimension of your latent space which is very uncertain, it doesn't make sense to kind of preserve a lot of bits for that, right? Whereas if there's another dimension of your latent encoding which has a very high degree of uncertainty, it certainly makes sense to kind of round less aggressively. And I think the advantage of our method is that we have like an uneven, essentially an uneven quantization grid, right? I mean, there are certain dimensions that we treat every dimension differently, right? And therefore we are really, and that actually ultimately also affects the behavior on the decoding side, right? I mean, because I don't know, certain dimensions might be very important for the reconstruction and other dimensions might be less important. I don't know if that answered your question.
Somewhat, yeah. Thanks.
Right. Any more questions?
Maybe just to follow up on Stephan's answer. So in our evaluations, we always use the deterministic decoding. So we kind of pretend that when we do compression, the model is no longer Bayesian. So we just, we just take the maximum likelihood reconstruction, basically taking the argmax of your X condition on Z as our reconstruction. So yeah, we didn't really consider the variability in the model output. If we kind of use different samples of Z and decode different X. I hope that helps.
Any more questions?
A great talk. Can I ask a quick question?
Sure.
So in the second paper, the variational Bayesian quantization paper, I'm just curious, comparing to the Ballet 2007, which pre-trained model is used? So I'm asking because it seems that the low bit pre-region lags, but the high bit region looks okay.
The high bit region looks okay, and the low bit region not so much. You're talking about this comparison, right? The dash, the solid orange curve compared to the dots here, right?
Right.
Yeah, I'm not sure if I have a good intuition here. Or you mean here on the right-hand side also, that that's even more pronounced. I don't know, Ivo, do you have a good answer?
So I think we picked a beta, so for our pre-trained VAE, to have kind of good overall rate distortion performance. And yeah, in this particular model, and actually in a lot of image compression results comparisons, it seems like the model's performance tend to differ a lot more in the low bit region. And it's the case for our model as well. Like you can also compare ours against JPEG. You can see the difference in the low rate case is also a lot bigger. Yeah, I don't have a straightforward answer as to why the discrepancy is higher in the low rate case. I guess the performance gain might be easier in that case than in the high rate regime, where your algorithm is forced to memorize more details of the image, versus in the low rate case, you kind of have more freedom as to what latent space how you interpret the latents and how you encode the latents. This is my intuition.
Thank you.
Thanks.
Okay, well, we're past 2 o'clock, so I should wrap up there. But I think let's all virtually thank Stephan again for a great talk. And hopefully I'll see you all next week when we have another great speaker lined up.
Thank you.